Hello? Okay, good evening all. So I think let's start today's class. So first we will see the first we will recap what sir have taught. So today is all about the welding defects. So performance of the welding structure depends on the quality of the fabrication and the presence or absence of the defects in the weld joints. Defects impair the strength of the weld joint and results in the failure of the structure. The principal cause of this failure follow requirements of the welding specifications, use of a substandards materials, defective welding equipment, and poor welding skills. So any compared to the any ideal parameters, if we use the any substandard materials or improper welding parameters or improper welding techniques, the welding defect generally arises. What kind of welding defects are we can classify as the one is the cracks, second is the cavities, next is the solid inclusions and incomplete fusion or penetration, imperfect shape, and miscellaneous defects. Okay, so such as the cracks means we can see any longitudinal cracks, transverse cracks, and we have seen plenty of cracks, liquidus crack and solidification cracks, hydrogen cracking, cold cracking. Those are such kind of things, and cavities, any porosities, and any foreign particle inclusions, incomplete fusion, incomplete penetration, or improper shape, or any other defects. These are the broader classifications. So we can classify these defects into two categories. One is the visible defects, and other one is the hidden defects. Visible defects are which we can identify with eye, and hidden defects are which are embedded in the weld bit. Okay, for example, in case of visible defects like surface cracks, deformations, wrapping, uh, and the incorrect bead profile, and dimensional inaccuracies, overlaps, undercuts, underfill, and extensive penetrations. All of these are the visible defects. Hidden defects are like which we cannot see is that lack of fusion, lack of penetration, blowholes, shrinkage cracks, slag inclusions, and tungsten inclusions are any coarser microstructure. All of these are the hidden defects. Okay. So from where these defects are coming is that one, improper selection of the process parameters, improper application of the welding processes, interaction of the weld metal with the prior defects, undesirable metallurgical structures, undesirable shape, size of weld bead, incorrect edge preparation, poor workmanship and supervision, and poor design. All of these are the source of welding defects. Okay. So some of the welding defects from the arc welding we can see like surface cracks, subsurface cracks, distortions, lack of fusion, incorrect welder profile, lack of penetration, blowholes, surface porosities, shrinkage, cavities, surface oxidation, inclusions, and excessive sputtering. All of these are the arc defects. Other welding defects like resistance welding, spot welding, seam welding, such kind of things we can see like resistance welding defects and friction welding defects. Those are also we can those are which are the not we can find out. Okay, these are the some of the cracks which we can crack defects how it looks like. Okay, cracks are due to the high concentration of the stresses. Because of the high concentration of the stress, we will see the cracks. Okay, poor fit up and incorrect welding process parameters. Those also will result in the cracks. poor edge qualities, and deeper penetration, and okay, all of this results in the cracks. Okay, so some of the incorrect weld profiles you can see. Here is the ideal weld profile how it should be look like. But we will see that this kind of profiles, these are all are the incorrect weld profiles, like insufficient root, excessive convexity, excessive undercut, size overlap, size insufficient lag, or incomplete fusion. All of these are the um, incorrect weld profiles. So other things are the surface porosity, surface oxidation. Uh, Surface oxidation is mostly prominent in the most oxidizing metals like titanium, magnesium, aluminum, and other alloys. Okay, uneven coarse rippling and excessive spattering. All of these are the defects. This is one of the defects is the slag inclusion. So during SMAW like sealed metal arc welding, the slag which we are using that may be entrapped into the weld bead. This is due to faster welding processor, other high current, those things we can see. And in a side in a submerged arc welding also this slag inclusion may occurs. Okay, and when coming to the porosities, there are the some other sub classifications are there, such as the uniform porosity, cluster porosity, liner porosity, and start and end porosity. These are the uniform porosities where we can see the porosity uniformly distributed among the weld bead, and cluster porosities where we can see the clustering of the porosities at certain regions, and line porosity we can see in a line we can see some kind of porosities, and start and end porosities where the starting and end portion we will see the some kind of porosities. Okay, when coming to the non-arc welding process like spot welding, we can see like excessive electrode inclusion. As you know, spot welding we will use the copper electrodes. The copper electrode may be included into the weld bead, and metal explosion and shrinkage voids, these are all are the defects in spot welding. So you can see the spot welding defect here. Here is the inclusion of spot welding. There is a porosity we can see here. Okay. Next we can see. So this is the ideally we want the weld as a this kind of thing, but generally we will not. So if there is some kind of as we discussed because of the improper weld material and improper weld parameters and proper welding techniques, we will get some kind of defects like cracks, porosity, crack, porosities, undercut, slag inclusions, sputtering, incomplete fusion, incomplete penetration, and overlap. All of these are the comes under the welding defects. So you can see the how the different welding defects are look like. So here is the porosity, inclusions, cracks, lamination tearing, slag inclusion, incomplete penetration, underfilling, sputtering, incomplete fusion. All of these are the welding defects. Okay, so now we will see the some of the problems. A welding defect is a best defined as a option A any visible imperfection, option B any discontinuity affecting performance, option C only surface irregularities, option D only internal flaws. So correct answer will be option B. It is the any discontinuous uh, affecting performance. Okay, because it is not only what is the visible, it is also including of the internal one. So both we combinedly we can call it as a welding defects. Welding defects not only appear in the surface level, we can see some other welding defects, hidden in the weld bead also. Okay. So a defect is discontinuity that compromises the service performance, whereas not all imperfections are harmful. Okay. Which of the following is classified as the surface defect? Option A porosity, option B slag inclusion, option C undercut, option C D lack of fusion. So in case of porosity, we will see at the middle of the weld bead. Okay. So you can see as here porosities we can see at the middle of the weld bead. So it is not visible. And similarly slag inclusion and incomplete fusion, these are the not visible, but undercut we can see from here, from the surface, so it will be a surface defect. Okay, so porosity not, slag inclusion not, lack of fusion not, so it will be the undercut. Undercut is the groove formed at the weld toe, visible on the surface and reduces the cross sectional strength. Porosity in welds is mainly caused by solution shrinkage, entrapment of the gases, high residual stresses, grain growth. Answer will be B. It is the entrapment of the gases. Gases like hydrogen, nitrogen, oxygen get entrapped during the solidification, forms the porosities, pores. Okay. Which of the defect caused by the improper fusion between the weld metal and the base material? Option A porosity, option B slag inclusion, option C lack of fusion, option D undercut. So correct answer will be lack of fusion. So lack of it is the it is happens due to low heat input, improper technique, or incomplete bonding between the layers. These are the reasons for the this improper fusion between the weld metal and base material. The slag inclusion is most commonly associated with the which process? TIG welding, MIG welding, SMAW, laser welding. So in slag inclusion comes from the entrapment of the slag. First slag where it is come from? It is come from the flux. So in given among the given options, which process will use the flux? So in TIG welding, we will use the shielding by argon gas. In case of MIG, also we can use the CO2 gas or argon gas or other gases. In laser welding also it is the a gas only. But is in SMAW shielded metal arc welding, the electrode contains the flux coating that will form the slag on a weld bead. So in this case only we will see the formation of the slag. So answer will be it is the SMAW. Flux in the SMAW process produces the slag which may get trapped if not removed properly. Okay. Next, which defect reduces the effective cross section area of the weld? Okay. So effective cross section area of the weld, which defect will reduces? Option A porosity, option B undercut, option C slag inclusion, option D all of the above. So first the word effective cross sectional area. So effective cross sectional area means what is the area of the metal that will contributes to strengthening of the component. If any defects are there, those will not contribute into the strengthening of the component. So any defects which will be considered as a loss of the um, effective cross sectional area. So all of these defects are and comes under this uh, loss of the cross sectional area. So all of the defects reduces the load bearing area, decreases the strength and reliability. Which of the following is a internal defect? Option A undercut, option B overlap, option C porosity, option D sputtering. As we seen previously, here only porosity is the inside one, sputtering, overlap and undercut all are visible. So answer will be the porosity. Porosity. Next, lack of penetration occurs due to why? So excessive heat input, insufficient heat input, high cooling rate, and grain refinement. Okay, answer will be B. Insufficient heat input. Low heat input prevents the full melting of the joint root that results in the incomplete penetration. Which of the following defects is mainly caused by the improper cleaning of the base material? What is it? Option A porosity, option B undercut, option C cracking, option D distortion. So answer will be porosity because any improper cleaning, the contamination like oil, rust, moisture releases the gases, causes the porosity. Okay. The distortion in the welding is primarily due to chemical reaction, residual stresses from uneven heating and cooling, gas entrapment, inclusion formation. So answer will be distortion is mainly due to the option B, residual stresses from uneven heating and cooling. Explanation: non-uniform expansion and contraction during the welding leads to distortion and wrapping. Okay, so some of the key points are porosity is caused by gas entrapment. It is the internal defect. Slag inclusion, flux due to the flux entrapment, that is also internal defect. Lack of fusion, it is due to the low heat input, that is also a internal defect. Okay, undercut, that is due to the excessive current, it is the surface defect, we can see from the surface. Distortion, it is due to the thermal stresses, it is geometrical defect. Next, which of the following is a surface defect? I think we have already seen, it is the option A porosity, option B slag inclusion, option C undercut, option D lack of penetration. The answer will be the undercut. Undercut appears the grooves along the weld toe and is clearly visible on the surface. Which of the following is a subsurface defect? Option A overlap, option B sputter, option C porosity, option D underfill. So correct answer will be subsurface defect means it is the internal defect, that will be the porosity. Porosity causes inside the weld metal due to the trapped gas and not always visible externally. Lack of penetration is classified as a surface defect, subsurface defect, only visible defect, not a defect. So answer will be, it will be the subsurface defect. It occurs at the root of the weld make it an internal defect affecting the joint integrity, which defect can caused by excessive weld current leading to groove formation. That will be option A, porosity, option B, slag inclusion, option C, undercut, option D, lack of user. So answer will be, it is the undercut. High current melts base metal excessively without filling. Okay. So the grooves form at the weld edges. This is forms the undercut. The slag inclusion is most likely occurs in the, I think this is also we have seen, which defect is characterized by metal flow, flowing over the base metal without fusion. Answer A, undercut. Option B, overlap. Option C, porosity. Option D, crack. So answer will be B. It is the overlap. Overlap is a surface defect caused by the improper techniques or lower traveling speed. Which of the following defects require non-destructive testing for detection? So, what is destructive testing is, in the testing we will break our sample and we can observe it. We have to observe it. But in case of non-destructive testings, we shouldn't to break the sample. Okay, then we can observe it. Uh, in So option A, undercut. Option B, sputter. Option C, porosity. Option D, overlap. So answer will be, it will be the porosity, because porosity we can measure by non-destructive testing like CT scan method we will use to measure it. Okay. Internal defects like porosity require radiography or ultrasonic testing for the detection. Lack of fusion is mainly caused by high heat input, low heat input, excessive filler material, high cooling rate. So answer will be, it is the low heat input. Insufficient heat prevents the proper melting and bonding between the layers, which defect reduces the fatigue strength significantly due to the stress concentration at the surface. So answer will be option A, porosity, option B, slag inclusion, option C, undercut, option D, internal crack. So it will be the undercut. So fatigue is mainly due to the surface conditions. So undercut will creates the grooves that will creates the stress concentration regions that will result in the fatigue failure. Surface defects like undercut acts as a stress risers and reduces the fatigue life. Which of the following combinations is correctly matched? Porosity, surface defect? No, because porosity is a internal defect. Slag inclusion, surface defect? No, it is also a internal defect. And undercut, subsurface defect? No, undercut we can see on the surface, so it is not a subsurface defect. Lack of penetration is a surface defect. Yes, because lack of penetration is the inside the bell bead, so it will be the subsurface defect. Lack of penetration occurs internally at the root. Others listed are the incorrectly classification. Okay. So some of the key points: the surface defects like undercut, overlaps, sputtering. Those are the visual. We can find out by visual visual inspection. So subsurface defects like porosity, slag inclusion, and lack of penetration, we can find out by non-destructive testers like ultrasonic testing, radiology testing, such kind of tests. Okay. Next, we will see the third lectures, some slides. Then we will come back to the stress concentration do occurs in the well, and as load increases, yield point may reduces soon as a point of the stress concentration. After a slight yielding, the maximum stress is transferred to another point of the weld. This continues until the stress distribution over the whole load carrying section is uniform. Such balancing of the stress distribution takes place under the static loads and does not affect final stress in the weld to considerable extent. Okay, so what kind of stresses we can find out is that we have a stress along some E I modulus of rigidity modulus of, these are all of the parameters which you have to consider. So some of the metal properties uh, are like modulus of elasticity, Poisson's ratio, modulus of the rigidity, moment of inertia, polar moment of inertia, and a section modulus. All of these are the metal properties important for the static load conditions. So loading can be tension loading, compression loading, bending, shearing, and torsion. Okay. So the working stress, what we consider is the working stress is the failure stress divided by safety factor. So suppose if I have a material component which is the failure stress is 1000 megapascals, assume, and if the safety factor is the 2, that means we have to divide it by 1000 by 2, that is the 500 megapascal is the working stress. Above that we shouldn't operate it. Okay. So modulus of velocity as Poisson's ratio, it is a lateral strain by longitudinal strain. Okay. Generally it will be the 0.25 to 0.35. Modulus of rigidity, the G we can get by, we have a formula that E by 2 1 plus mu. Okay. Moment of inertia, moment of inertia, it is the opposite sum of the properties by modifying. So how we can, what is the formula for the modulus of inertia? I equal to BD cube by 12. It is from the neutral axis. If it is from the baseline, we can find out by BD cube by 3. Similarly, we have a polar moment of inertia that is denoted by J, and torsional resistance, that is the WT cube by 3, and angular rotation that we find out by TL by ER. E is the modulus of the velocity, L is the length of the flying surface, T is the torque, and R is the torsional resistance. So polar moment of inertia J we can get by sum of the any two movement of the inertias along the axis of the right angle to each other. J equal to Ix plus Iy. Okay. And sectional modulus, the race of the moment of inertia with respect to the linear equiaxis divided by the that is the Z equal to I by C. Okay. Next, a component of the or structure surviving a single applying load application of the load may fracture if the same load fluctuates. The fatigue failure occurs as the brittle fracture produced by the cyclic stresses usually below the elastic limit of the material of the component. The fatigue stress may be of type bending, axial, torsional, and combination of those. Okay. So, characteristics of the fatigue failure occurs in the three stages. Initiation of the crack usually starts as a micro cracks because of the stress cycling results into the altering the displacement of the metal along slip planes. Slow growth of the crack, fracture. A fatigue crack is a transgranular. So it is fatigue happens not at the grain boundaries, but it will cut through the grains itself. So how it will start? It has the three stages. One is the initiation of the crack. So usually starts at the micro cracks at the surfaces. So how the fatigue happens is that suppose if I have a one beam, I'm applying the applying certain deflection from this direction and this direction, but these are within the its elastic property limit. But when we see at this location and this location, you will see that the once we compare from the here, if you make a one straight line, okay. So here we will see a very maximum tensile stress, and here we will see the maximum compressive stress. So due to this tensile stress, the crack initiation will start. Micro cracks will be formed here. So once we coming to the this region, then it will be reversed. Here it will be the compressive stress, and here it will be the tensile stress, maximum tensile stress. And again here it will be the micro crack will start. And if we repeat this cycle continuously, the stress concentration will become more and more, and it will start failure as a fatigue failure. Okay. Usually starts a micro cracks because of the stress cycling resulting into the altering the displacement of the metal along the slip planes and slow growth of the cracks and fracture. Okay. So this is how the stress concentration micro crack look like, and it will propagate. And this kind of cracks we can observe in the mm, material. So how we can find out this fatigue life is that by using a SN curve. S is the stress value, N is the number of the cycles it is applied. Okay. There are two classifications are there, like high cycling low stress factor, or second one is the low cycling and high stress factor. So if we apply the low stress value but applying multiple a huge number of the cyclings, that is then failure occurs, that is called as a high cycle low stress fatigue. And if I apply the high stress but number of the cycles are the low, then the failure happens. It is called as a low cycle high stress fatigue. Okay. So factors affecting the fatigue lives are material properties, joint configuration, stress ratio, welding procedure, load concentrations, residual stresses, environmental effects. All of this will be affects the fatigue life. Okay. Here we can see it is the longitudinal welding and transverse welding positions. Here we can see transverse welding and longitudinal welding positions. How we can improve the fatigue life of a material? What is that? How we can improve? Improve the design of the weld procedure and improve the surface compressive stresses. Incorporate this and introduce the surface compressive stresses and protection from the atmosphere like prevention of the corrosion and so on. All of this will improve the fatigue life. So this is the tensile loading condition for the design for the compressor loading. We had to prevent it from the buckling of the happening so that it will have a much more compressive strength and bending. We can find out by bending loading. We can find out by this formula m by I by r and sigma by. Here is the and the strength and the stiffness of the beam. It is the strength is directly proportional to the load by elongation, that is that is directly proportional to EI, and torsion loading that we can find out by R equal to WT cube by 3. Here is the R is the transitional resistance, W is the width of the flat section, T is the thickness of the flat section. So angular twist theta we can find out by T into L by ESR. T is the torque, ES is the modulus of the elasticity, T is the torsional resistance. Okay. So the fatigue loading you can find out. So there is a two loading condition F1 and F2. N is the number of the loads, number of the cycles. So if I want to know the load which how much load it can sustain, the one that we can find out by F2 equal to F1 and 1 by N2 into K. Here K is the 0.13 general. Okay. So there is the different kind of stresses, cyclic stresses may present. Suppose if it is the only tensile stresses, that means it is the neutral, where all happening are in the tensile stresses. Or we can have a different another configuration where we can have a tension, compression, tension, compression, tension, compression like this way. Or we can have a some residual tension that we can call it as a half tension region. So we can have a cyclic loading from that. Here is the S mini, S max we will have. Here is the X max and 0. Here is the X max and X mini. Here X mini will be the compressive stress. Here X mini also the tensile stress only. For non-ferrous materials, it will be the it looks like this way. SF is the unnotched fully fatigue. Next, performance of the welded structures depending on the quality of the fabrication. That is the presence. First, we will see the problems. Then we will come back to the this one. In welding joint under static loading, the primary design objective is to maximize the hardness, minimize the residual stresses, ensure the adequate strength and load transfer, optionally reduce the weld metal volume. So answer will be it is the C. Ensure the adequate strength and load transfer. Design must be ensure the joint can safely carry the static loads without failure, considering the strength and geometry. Which type of the weld joint is most effective under the static tensile loading? Lap joint, butt joint, corner joint, edge joint. So it will be the butt joint. Butt joint provides the uniform stress distribution and full cross-sectional strength. The fillet welds are primarily designed based on the weld length, throat thickness, reinforcement height, heat input. Answer will be fillet weld will be throat thickness. Effective load bearing area in fillet welding equal to throat area, which determines the strength. Which of the following weld orientation is most favorable under the static loading? Eccentric loading, bending loading, axial loading, torsional loading. Answer will be axial loading. Axial loading produces the uniform stress distribution, minimizes the stress concentration. Stress concentration in welded joint is mainly caused by smooth surfaces, uniform geometry, sharp notches and discontinuities, low heat input. So answer will be the sharp notches and discontinuous. So geometric discontinuities like weld toes act as a stress risers, increasing the failure risk. Which design practice reduces the stress concentration in weld joints? Sharp corners, smooth transition and proper contours, increasing the residual stresses, or reducing the weld size drastically. So answer will be smooth transition and proper contour. The smooth geometry reduces the stress concentration and improves the static strength. In fillet weld, the failure under the static loading usually occurs at weld reinforcement, weld toe, throat section, and base metal far from the weld. Correct answer will be throat section. The throat is the weakest cross section and carries the maximum shear stress. Which factor is the most critical in designing the welds for the static loading? Color of the weld, residual stresses only, load direction and magnitude, and welding speed. So answer will be C. It is the load direction and magnitude. So design must be considered how the load is applied to ensure the proper strength and safety. Eccentric loading in weld joint leads to uniform stresses, only tensile stresses, combined stresses like bending plus shear, no stresses. Answer will be combined stresses, bending plus shear. So eccentric loading introduces the bending moment plus shear increases the failure risk. Which of the following improves the static strength of the weld joint? Option A, undercut formation. Option B, increasing weld effects. Option C, proper joint design and alignment. Option D, high cooling rate. So answer will be proper joint design and alignment. So good design ensures the proper load distribution, minimizes the stress concentration, and that results in the higher static strength. So some of the important points: butt joint best for the tensile loading, fillet weld throat governs the strength, axial loading, uniform stress distribution, eccentric loading, bending plus shear, and smooth geometry reduces the stress concentration. The fatigue failure in the weld joint is primarily due to single overload, repeated cycle loading, high temperature, corrosion only. Answer will be fatigue due to repeated cycle loading. Fatigue occurs due to repeated stress cycle even when stress is below yield strength. The fatigue crack in weld joints usually initiated at weld center, base metal interior, weld to fusion boundary center. Answer will be it is the weld to. The weld to has the high stress concentration, makes it the most common crack initiation site. Which factor is the most significant effect on fatigue strength of the weld joints? Option will be A, color of the weld. Option B, surface finish and geometry. Option C, weld speed. Option D, arc voltage. So answer will be the surface finish and geometry. So fatigue strength highly sensitive to surface irregularities and notches, unlike the static loading. The residual tensile stresses in welds, option A, improves the fatigue life, have no effect. Residual reduce the fatigue life and only affect the corrosion. Answer will be reduces the fatigue life. Reason, residual tensile stresses added to the applied stresses that will accelerate the crack initiation and growth. Which method improves the fatigue life of the weld joints? Increasing the welding defects, Short pinning, increasing the residual tensile stresses. Rapid cooling. So answer will be the short pinning. So short pinning introduces the compressive surface stresses that delay the crack initiation. In fatigue loading, weld joints generally fail at high strength region, low hardness region, region of the stress concentration, center of the weld metal. So answer will be the region of the stress concentration. The fatigue cracks initiate at the stress risers like weld toe, undercut, and defects. Which type of the weld has the better fatigue performance? Rough weld surface, weld with undercut, smooth and ground weld, weld with slag inclusion. So answer will be C. It is the smooth and ground weld. Smooth surfaces reduces the stress concentration and improves the fatigue resistance. Next, the fatigue strength of the weld joint compared to the base metal is generally higher, equal, lower, unaffected. Answer will be it is a lower due to stress concentration, residual stresses, and welding defects. Which parameter is most relevant for the fatigue design? Yield strength, ultimate strength, stress range, hardness. Answer will be stress range. The fatigue lies depending on the stress amplitude and range, not just the maximum stress. Which of the following reduces the fatigue crack initiation? Sharp weld toe, undercut, toe grinding, high residual stresses. So answer will be toe grinding. So toe grinding smoothens the geometry, reduces the stresses, concentration, improves the fatigue life. Factors: weld toe, effect on the fatigue, crack initiation side. Residual tensile stresses reduces the life. Surface finish is critical. Short pinning improves the fatigue resistance life. Stress range governs the fatigue. Okay. Next, let's see the performance of the welded structures depending on the quality of the fabrication, that is presence and absence of the defects in the weld joints. Defects impairs the strength of the weld joint and results into the failure of the structure. The principal causes are the failure to the following requirements of the weld specifications: use of the substandard materials, defects in weld and poor weld skills. I think this we have seen. So let's see the problem. The combined concentration of the static and fatigue loading, the most desirable weld features is sharp weld toe, smooth counter and gradual transition, excessive reinforcement, and, and irregular geometry. So answer will be smooth counter and gradual transition. Smooth geometry reduces the stress concentration, improving the both static strength and fatigue life. Which joint design is the most suitable for the both static and fatigue loading? Option A, lap joint with filler weld. butt joint with the full penetration, edge joint, spot welding. Answer will be butt joint with full penetration. Uniform stress distribution. It provides the uniform stress distribution and minimal stress concentration. The fatigue critical applications, the weld reinforcement should be option A very high, option B completely absent with smooth finish, option C irregular, option D extremely thick. So answer will be completely absent with smooth finish. Excessive reinforcement acts as a stressorizer and reducing the fatigue life. Which loading condition is most critical for the fatigue failure? Static compressive loading, static tensile loading, cyclic tensile load, and constant temperature. Answer will be cyclic tensile load. Fatigue cracks initiate under the repetitive tensile stresses, especially at the stress concentrations. Which design practice improves the both static and fatigue performance? Option A introducing the sharp corners. Option B avoiding the welded effects. Option C increasing the residual stresses. Option D using the discontinuous welds. So correct answer will be avoiding the weld defects. Defects act as a crack initiation site that will harmful for both static and fatigue loading. Which weld location should be avoided in the fatigue critical structures? Option A neutral axis, option B low stress region, option C high stress region, option D compressor zone. So answer will be high stress region. Wells in the high stress regions are more prone to fatigue cracking initiation. Eccentric loading in the well joints leads to uniform stresses, only shear stresses, combined bending and shear, the no effect. So correct answer will be combined bending and shear. Eccentric loading introduces the complex stresses states, increases the failure risk. Which both features is most critical for the fatigue design but less critical for the static design? Option A load magnitude, option B material strength, option C surface finish, option D cross section area. So answer will be surface finish. So fatigue is the highly sensitive to surface irregularities, unlike the static loading. Which method improves fatigue performance without significantly affecting the static strength? Option A increasing the well defects, option B short pinning, option C increasing the weld size excessively, option D rapid cooling. So correct answer will be short pinning. Short pinning introduces the compressive stresses, delaying the fatigue crack initiation. For static loading, Weld strength is mainly governed by surface finish, stress range, excessive throat area, residual compressive stresses. Answer will be effective throat area. The static strength depends on the load bearing cross section area, especially in the fillet welds. So, some of the key points are smooth geometry improves the static loading, important for static loading, also critical for the fatigue loading. Weld effects reduces the strength in static loading, particularly initiate the cracks. Surface finish is less critical for the static loading and highly critical for the fatigue loading. The throat area governs the strength in the static loading and less dominant in the fatigue loading. Residual stresses has the moderate effect on the static loading and strong effect on the fatigue loading. Okay.